Section 3.1, Basic Functions and Their Graphs. Our goals for this section is to be able to create a table of values and sketch the following basic functions: the square function, the cube function, the square root function, the cube root function, the absolute value function, the reciprocal function, and the identity function. We're also going to discuss things like domain and range of each of those functions. We want to be able to identify the symmetry of a function. We'll describe a couple of different types of symmetry we want to be able to identify. We're going to be able to determine any extreme values of a function, and we're going to learn how to use a graphing calculator to determine things like the extreme values of a function and any zeros of a function. Alright, so let's start with the square function. So this function takes the input and outputs the square. So let's start by just kind of choosing some inputs. Now there's no restrictions on this because we can square any number. So I'm going to go with -3, -2, -1, 0, 1, 2, and 3. Alright, so if there are my inputs, let's square them. My outputs would be 9, 4, 1, 0, 1, 4, 9. And we can plot those points. -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. And so we get this shape, and you might recognize this shape. It's called a parabola, and it would continue onward in either direction. So we get a graph that looks roughly like this. Alright, so there's the graph of the square, a table of values and a graph for the square function. Let's note the domain and range. The domain of the function is -infinity to infinity, and the range of the function is 0 to infinity. And we would include a bracket on the 0 because we can get that exact number as an output. The cube function, f of x is equal to x cubed. Again, we can put anything we want into this, so I'm going to choose, again, the same that I did for the square function. So let's see, -3 cubed is -27, -2 cubed is -8, -1, 0, 1, 8, and 27. Now we won't plot the points for -3, -27, and 327, but let's plot the others. Let's see, -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. Now if we wanted to, we could sort of think, well, -3, -27 is going to be way down here somewhere, and 3 + 27 is going to be way up here somewhere. And so we see how that curve increases rapidly. Alright, so let's draw the curve that passes through those points. Alright, so there's the cube function. Let's find the domain and range. Well, this continues all the way to the left and all the way to the right, so the domain is -infinity to infinity, and the range all the way from the bottom to all the way to the top, also -infinity to infinity. The square root function, f of x is equal to the square root of x. Now we have restrictions here. Recall that if we're dealing with real numbers, we can't have negative values under the radical. So I'm going to start with 0, and then I'm going to choose numbers carefully so that my outputs will be nice. I'm going to choose 1, 4, 9, 16, 25. I'm choosing perfect squares because they have nice square roots. So if I choose 0 as my input, the output is 0. If I choose 1 as my input, the output is 1, 2, 3, 4, and 5, etc. Now remember, I can't have any points that have negative x values for this graph. So I have 0, 0, 1, 1, 4, 2, 9, 3. My next point would be, what, 16, 4, which might be about, out here somewhere. So for the graph, we kind of start at 0, 0, and we only move to the right. So there's the graph of the square root function. Let's determine its domain and range. The domain, it starts at 0 and goes to positive infinity. The range, thinking of the outputs, also starts at 0 and also goes to positive infinity. It's going to continue to increase as we move to the right. The cube root function. Now we don't have any restrictions on the cube root function like we did for the square root, because we can find the cube root of negative numbers. So I'm going to go with inputs that are perfect cubes, as they will have nice cube roots. Negative 27, negative 8, negative 1, 0, 1, 8, 27. The corresponding outputs then would be negative 3, negative 2, negative 1, 0, 1, 2, and 3. Now again, just based on the scale of my grid, I'm not going to plot the 27s. Let's see, negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. And the graph would continue to increase as we move to the right. All right, so let's draw the curve that goes through those points. And so there's the graph of f of x equals the cube root of x. Domain, it goes all the way from the left to all the way to the right. So negative infinity to infinity. Range, it will eventually get to very large negative numbers for the output and very large positive numbers for the output. The absolute value function. So this function takes the input and returns the absolute value of that input. There are no restrictions on this function for domain. So let's go with negative 4 to positive 4. The absolute value of negative 4 is 4. The absolute value of negative 3 is 3. 2, 1, 0. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2, etc. We'll plot these points. And we get this V shape. Each of those parts of the absolute value are straight. So I'm using a straight edge to draw this. So there's the absolute value function, table of values and graph. The domain is negative infinity to infinity. I can put any number into this function. And the range is bracket 0, infinity. The reciprocal function, f of x is equal to 1 over x. So this function takes the input and finds its reciprocal. So I'm going to choose some interesting numbers, I suppose. I'm going to start with negative 10, negative 1, negative 1/2, negative 1/10. And how about 0? Let's see what happens if we put 0 in. And then I'm going to choose, for positive numbers, 1/10, 1/2, 1, and 10. Alright, so if my input is negative 10, its reciprocal is negative 1/10. If my input is negative 1, its reciprocal is negative 1. If my input is negative 1/2, its reciprocal is negative 2. And if my input is negative 1/10, its reciprocal is 10. Sorry, negative 10. 0. What's the reciprocal of 0? Well, 1 over 0 is undefined. 0 is not in the domain of this function. If my input is 1/10, its reciprocal is 10. If my input is 1/2, the reciprocal is 2 and 1. And if my input is 10, the reciprocal is 1/10. So let's plot these points. I have negative 10, negative 1/10. So that's going to be really close to the x-axis. I have negative 1, negative 1. Oops, I plotted that first point on the wrong side of the axis. Sorry about that. Let's start again. Let's plot the point negative 10, negative 1/10. So that would be about here. Then I have the point negative 1, negative 1. I have negative 1/2, negative 2. I have negative 1/10, negative 10. So that's going to be really close to the y-axis. Now, when x is 0, the function is undefined. There is no point on the curve when x is 0. All right, now let's look on the other side. When x is 1/10, y is 10. So again, really close to the axis. We have 1/2, 2. We have 1, 1. And we have 10, 1/10. So now I'm going to draw the curve that connects and goes through these points. Now we could plot some other points if we wanted to, but what generally happens is, coming from the left, the curve starts very close to the y-axis, to the x-axis, and then very slowly decreases until we get near negative 1, negative 1, and then it begins to rapidly decrease. And it gets very close to the axis. It doesn't actually touch the axis, though, because remember, when x is 0, there's no y value, so there cannot be any point. So then the curve kind of jumps over that x value of 0 and comes back. It comes up here to the top and follows the rest of the points. It's still decreasing very rapidly until we get to 1, 1. And then it begins a very slow decrease. So now this function has some interesting features. It has what are called asymptotes. This line has a vertical asymptote at x equals 0. So we have this, and we usually denote it with a dotted line. We have what's called a vertical asymptote at x equals 0. So I'm drawing that in red. There's a vertical asymptote at x equals 0, and we have a horizontal asymptote at y equals 0. Now these asymptotes are lines which the curve gets close to but never crosses. Alright, so we have a vertical asymptote at x equals 0. We have a horizontal asymptote at y equals 0. The domain of this function is a little tricky to write. The domain goes from negative infinity to 0 and then union 0 to infinity. So it skips over 0, but everything else is included. And the range is exactly the same for this function. Negative infinity to 0, union 0 to infinity. And finally, we have the identity function. So this function says your output is the same as the input. So if I choose negative 3 to 3 by 1s, my output is exactly the same. And notice that this is a line. This is a linear function. So there's the identity function. It has domain negative infinity to infinity and range negative infinity to infinity as well. Each of these following graphs is a transformation of one of the basic functions that has been presented. Determine that basic function. So we want to be able to look at a graph and say, well, that looks like one of those basic functions. Which one? Alright, so let's see. This first graph is always decreasing. It's not a line. It's not a parabola. This is a transformation of the cube function, x cubed. So remember, the cube function looks roughly like this. So this one appears to have been sort of flipped over, moved to the right, and moved up. Our second graph, notice it has a starting point but doesn't continue to the left. Which function does that? The square root function. Remember, the square root function looks roughly like this. So that looks like a square root function. It's been shifted right and up, but it looks basically the same. And I don't think there's any way to mistake this graph. Notice how it appears to have an asymptote, a horizontal and a vertical asymptote. There's only one function we've seen that does that, and that's the reciprocal function. F of x is 1 over x. This one appears to have been moved left and down, but it is the same basic function. Let's talk about symmetry of functions. We will discuss two different types of symmetry for this course. We have what's called an even symmetry and an odd symmetry. We say that a function is even if the function exhibits symmetry about the y-axis. So that means, if I think of the y-axis here, notice that there's a symmetry about that line. I could flip the curve over that line that I've drawn in orange and it would match up exactly. That is even symmetry. When that happens, f of negative x is equal to f of x. And that's one way that we can test a function for even symmetry. We say that a function is odd if the function exhibits symmetry about the origin. So the origin is 0, 0. When we say origin about the symmetry, that means if I were to take this and sort of flip it over 180 degrees, if I were to rotate that part of the curve 180 degrees, it would match up exactly. That is origin symmetry. And an odd function exhibits origin symmetry. And when that happens, f of negative x is equal to negative f of x. So there's the test for odd symmetry. So notice for both of those, we substitute negative x into the function, and then we see what happens. And so when we want to find out if a function is even or odd, and we don't necessarily know how to graph it, we can substitute negative x into the function and see what happens. So let's take an example. Determine if each of the following functions is even, odd, or neither. Alright, so to do that, we find f of negative x for the function. Alright, so let's see. F of negative x would be 2 by negative x to the 4th power plus 3 by negative x to the second power. I've substituted negative x for x in in the function. So now what happens if I take negative x and I raise it to the fourth power? Well, let's see, that would be negative x times negative x times negative x times negative x. Negative times a negative times a negative times a negative is positive, and x times x times x times x is x to the fourth. So that would be 2, and then we'd have an x to the fourth. Similarly, negative x squared means negative x times negative x, which is x squared. And so notice that f of negative x is the same as f of x. We got back to where we started. And so therefore, f of x is even. Since f of negative x is equal to f of x, we have an even function. Let's consider the next example. F of x is equal to 7x minus 3. All right, so then f of negative x is equal to 7 times negative x minus 3. Well, that negative x is, it's only raised to the first power, so we would just multiply, and so that would be negative 7x minus 3. Is this equal to f of x? No, it's not, because f of x was 7x minus 3, and this is negative 7x minus 3. So it's not equal to f of x. Is it equal to the opposite of f of x? Well, let's see. The opposite of f of x would be the opposite of 7x minus 3, which would be negative 7x plus 3. So it's not equal to negative f of x either. So it is neither of these. F of x equals 7x minus 3 does not exhibit even or odd symmetry. It is not an even or odd function. Alright, what if f of x is equal to x times the absolute value of x? Well, then f of negative x would equal negative x times the absolute value of negative x. What's the absolute value of the opposite of x? What's the absolute value of negative x? Well, the absolute value of negative x would still be the same as the absolute value of x. And we just still have this negative x on the outside. Notice how that's the opposite of f of x. So this function is odd. And we can verify these. Let's take a quick look on the calculator. Alright, so on the calculator, let me graph that first equation, that first function. Y equals 2x to the fourth plus 3x to the second. I'm just going to graph that in the standard window. And notice it does appear to have that symmetry. It does appear to be even. It has that symmetry about the line, about the y-axis. Alright, and let's check y equals x times the absolute value of x. Now the absolute value, there's a couple of ways to get to it. Under the math menu, and we move to the right to number, and there's the absolute value. So x times the absolute value of x, let me graph that, and we get this graph, and it does appear to have that symmetry, that origin symmetry. Alright, so here's the summary of those basic functions that we've discussed so far. And I just took this right out of our textbook from section 3.1. So this summary gives the function, its graph, the domain, the range, and the symmetry, if it has any symmetry. So we've already discussed the domain and the range in the graph. So the things that you might want to add, you might want to go back to those graphs that we did earlier and note that x squared is even, x cubed is odd, the square root function is neither, The cube root function is odd. The absolute value function is even. The reciprocal function is odd. And the identity function is odd. Finding relative maximum and minimum values. So when dealing with graphs of functions, the relative maximum or minimum values are found at the turning points of a function. So those are the points where the behavior of the function changes from increasing to decreasing or vice versa. So if we look at this graph here, this point, see how this point is a turning point and it produces a relative maximum. We could also say that this point is a turning point and produces a relative minimum. So here, this point produces a relative minimum, and there's a relative maximum. But now understand that the relative minimum or maximum is the value and will be f of whatever that input is. It's the output, not the input of the function. Okay? The maximum occurs at x equals, in this case, x equals a. It occurs here, but the actual maximum value is f of a. So it's something to be careful about. So let's see an example. We have this graph, and we're asked to use the graph of the function to answer the following. Let's find the domain and range. Alright, so let's see the domain. We see that we have a minimum value, but no maximum value. So the domain is -5, and it's connected everywhere in between -5 to positive infinity. The range. Do we have a minimum value? Yeah, we appear to have a minimum value at -3, and it continues upward and covers everything. So the range would be bracket -3 to infinity. We're using a bracket because it includes that exact value. Alright, let's determine the increasing and decreasing intervals. Alright, so let's see. The function appears to increase in several places. Alright, so it's increasing. Remember, when we're talking about increasing or decreasing, we don't include endpoints. So it's increasing on -5 to -4. And remember, when we describe increasing and decreasing, it's always in terms of the input. It's decreasing again on -2 to 0. And it's increasing again on -3 to infinity. It's decreasing on -4 to -2, union 0 to 3. Find the relative minima. So minima is the plural of minimum. Are there any relative minima? So we're looking for turning points that result in a minima, or minimum. We have one here, one here. So we have a relative minimum. Remember, the minimum is the output. Okay, so we have a relative minimum of -2 at x equals -2. We have a relative minimum of -3 at x equals 3. Find the relative maxima. Again, we're looking for turning points that create a high point. There's one, and there's a second. So I have a relative minimum of 6 at x equals -4. I have a relative minimum of 0 at x equals 0. So those are all the relative. Now, absolute, when we talk about an absolute minimum or maximum. That's over the entire graph. So not just nearby. Relative just means nearby. Absolute means over the entire graph. So is there an absolute maximum? Well, we might be tempted to say that this point is the absolute maximum, or has the absolute maximum. It's the highest point on the graph. Well, wait a second. We have this arrow saying that this graph continues to move upward. And that part never ends. So there's no absolute maximum. Is there an absolute minimum? All right, and in fact there is an absolute minimum. There is a lowest point on this curve, and it is -3 at x equals 3. Finally, let's use a graphing calculator to determine any relative maxima or minima and the zeros of f of x. We'll talk about what the zeros mean momentarily. We know what the maxima and minima mean. So let's bring up our graphing calculator, and let me clear out my old function and put in my new function, x to the third minus 5x to the second plus 3x plus 3. I'm just going to graph that in the standard window, and I get this graph. Let me pull that graph down onto our screen so I can annotate it. Alright, so there's that graph of the function. I see a relative maximum, a relative minimum, and I see 1, 2, 3 zeros for the function. So now let's use the graphing calculator to calculate those values. Let's first find the relative maximum. Alright, so I've got the graph on screen. I'm going to go into the Calc menu, which is second in the trace key, and I'm going to use the maximum function. Hit enter. So now the maximum function, to use it, you want to kind of go where you think the maximum is. Move a few points to the left. Hit enter. Gives it a left boundary. Move to the right. Go past where you think the maximum is. Hit enter a second time. And now it's asking for a guess. Go close to where you think the maximum is and hit enter a third time and let it run. And it appears that the maximum occurs at 0.33333, etc., 3.481485. Alright, so the maximum appears to be at 0.33. Okay, so the maximum value is 3.48. Alright, so we have a relative maximum of 3.48 at x equals 0.33. That's what the graph told us. Let's find the minimum. Go into the second, Calc, choose the minimum command. Hit enter. Let me scroll to the left. I'm going to stay left of where I think the minimum is and hit enter. Move to the right. Go past where I think the minimum is. Hit enter a second time. Move towards where I think the minimum is. Hit enter a third time. And the minimum appears to be exactly 3, -6. So a relative min of -6 at x equals, what was it, 3? Yeah, 3. 2.99999, that's 3. Now what about the zeros? Alright, so go back to the Calc menu and you'll see the 0 command, which is the second option. And the 0 command sort of works like the minimum and maximum commands. Let me go to that first 0, which is between 0 and -1. So I'm going to move left of where I think it is, hit enter. Move to the right, and make sure you go past it. Make sure the sign on the y value changes. Hit enter a second time. Go back closer to where you think it is and hit enter a third time. And so I have a 0 at approximately negative 0.51. So zeros at x is approximately equal to negative 0.51. What about the next one? Repeat the process. Second, calc, the 0 command. We move to the right. I'm going to stay a little bit to the left of where I think the 0 is. Hit enter. Move to the right. Go past where I think it is. Hit enter. Move closer to it again. Hit enter a third time. 1.43. And x equals, there's one more. Stay a little bit to the left of the 0, hit enter. Move to the right, go past where I think it is, hit enter a second time. Go closer to it and hit enter a third time. And 4.09. Alright, so there's how we can find relative maxima, minima, and zeros using the calculator. That concludes the presentation for section 3.1.